got the space colonization blues. I got the space.
Jerry O'Neill, a physicist from Princeton University, published in September of 1974 the results of what a sophomore class concluded from the question Professor O'Neill asked. What can we do with the problem with Earth with increasing population and decreasing resources? The class concluded, colonize space. Model 1, twin rotating cylinders holding 10,000 people. Model 2, twin cylinders with 100,000. Model 3, twin with 1 million. Model 4, 10 million. Jerry O'Neill was the technical director of our summer study. This was the cover of the December 1974 issue of Physics Today, where it was published. I'm Harry Jebens and was a participant of the design study in 1975. I was an associate professor of civil engineering at the University of Wisconsin-Platteville. My background was in water and wastewater. My master's from Madison was a dual degree in sanitary engineering and hydraulics. My PhD, also from Madison, was in sanitary engineering. In 1974, when I applied for design study, EPA had just formed. The goal of EPA was zero discharge by 1985. I stated in my application, I do not think that the timeline for EPA goals is realistic. Your problems sounds definitely more difficult. Dick Johnson, Chief of Biosystems Division of NASA Ames, was a co-director, as was Bill Verplank, a faculty member in mechanical engineering from Stanford University. This is the report that we published, NASA 413. Participants of the study were 19 faculty members from around the country, 6 students, and we had some visitors over the course of the summer. One of the students from MIT was Steve Brody, a recent master's graduate in physics, and Lawrence Winkler, a recent graduate in aeronautics and astronautics. Wink and Steve produced Space Colonization Blues, which didn't get in the report, but you can get it separate.
Nothing to lose, paying my dues to those space colonizing blues.
Our support staff for the summer, Linda Starr on the left was our secretary. That summer, she was living in the hull of a concrete sailboat in San Francisco Harbor. She and her husband were planning on sailing to Tahiti. Anybody know where she is now? With her is Vera Bushra. Vera was the NASA administrative assistant to Dick Johnson. After this, she joined Dr. John Billingham in SETI, the Search for Extraterrestrial Intelligence, and basically ran that program for John. Also that summer, Bonnie Dalton, the scientist, worked with us and was my support staff for years. There's Bonnie with her new Porsche recently in the hills above San Francisco. The objective of the summer design study was to design a city in space for 10,000 people. We wanted to be physiologically safe. That drove the configuration of the design. We wanted to be socially viable. We could thank Gordon Sutton of the University of Massachusetts Amherst, our sociologist, and Martin Ginsburg of Williams College, who provided the economic justification, and using near-term technology. Where would it be? This slide shows the libration points, gravity fields in the Earth-Moon system. L1, L2, and L3 are gravitational peaks. The objective there would stay there. L1 is between the Earth and the Moon. L2 is behind the Moon. L3 is in the lunar orbit on the other side of the Earth. L4 and L5 are gravitational valleys. They could be orbiting. We selected L5 as where we would put the space colony. It's easier to get to from the Moon due to its rotation. L4 In 75, we said leave it to the Russians. Maybe today we should say the Chinese. Also shown on the slide is geosynchronous orbit. An object in geosynchronous orbit would appear above the Earth to be stationary. An object would rotate around the Earth once a day. Mission overview shown in this slide. From low Earth orbit, transit to the Moon, to construct a mass driver. Raw lunar material collected from the lunar surface would be collected behind the Moon at L2. Raw material transported to the colony site, refined and used to construct the space colony. Satellite solar power stations would be produced for the economic justification and moved to geosynchronous orbit. This slide shows materials and their sources. Lunar soil provides all the metals needed to construct the space colony. What's not available from the lunar surface are the elements needed for life: carbon, hydrogen, and nitrogen. To survive, man needs gravity. Space missions that demonstrate without gravity the human body loses bone calcium, electrolytes, and quit producing red blood cells. Also, space nausea is a problem. What gravitational field is required? Because of the unknown, we said 1 gravity. Rotational producing gravity. What rotation rate? We said 1 RPM. To provide 1 gravity and 1 RPM, your habitat is 1,000 meters in radius. Details of this are in the report, but basically what we said in design criteria was Earth-like for radiation exposure, the atmosphere 1/2 pressure. Nitrogen must be transported. There is a need for inert gas in the atmosphere. This is our habitat. They call it the Stanford Torus. Picture a bicycle mile over a mile in diameter where people live in the inner tube that rotates. The radiation shield, about 1 meter of concrete equivalent waste products from producing the colony, provide radiation protection. Sunlight through a system of mirrors and enters the habitat to provide light. My part of the study was dealing with the life support requirements. To survive, the human body needs oxygen, water, and food. Expels carbon dioxide, water, and waste. I spent a lot of time chasing the carbon, hydrogen, oxygen, and nitrogen atoms around the system. Again, look in the report. With a dual water supply, water condensed from the atmosphere would provide potable water and irrigation water. Waste processing in the lower left would be wet oxidation. Schematic for the wet oxidation process. In 1975, I had a quote from John Mandela of Zimpro Wausau for 3 units FOB delivered to Cape Kennedy in the year 1995. The agricultural system area would be utilize a stack system as shown in cross section here. The sketch Chris had of the agriculture area, looking across it, in the distance you see a city. I thought it lost something when it was painted. Well, a space hawk and the cattle. July 1976, National Geographic published an article about our study. Asimov wrote it, and the cattle came back. A view of the residential area. This was produced by Pat Hill. He was part of our summer design study on the architectural faculty of San Luis Obispo. And although your world is only a football field wide, you have long lines of sight. Again, from the National Geographic article, you see that it looks a lot like a shopping center, but notice the trees are fruit trees, women and children. No one has to work nights. There are 3 cities. There's always a bar open. Food supply, we assume that 1/4 of the protein would be provided by fish, rabbits, chicken, and cattle. Shown here is the number of herd size per person and the amount of harvest per day. All participants and members of the space colony must have multiple skills. My job would be to help harvest the fish. I don't know if I could catch 700 a day, but if that's a limit, that's what I'd go for. This trout was about 6 years old in the Uinta Mountains of Utah, but in space, under ideal conditions, after 1 year, it'd be over 4 pounds. Someone also has to run the brewery. Tough job, but that'd be mine. It's 5 o'clock somewhere, 3 cities, 3 time zones. No one has to work the night shift. What does it take to get there? This shows the construction labor force. 6 years of research and development. 4 years to produce the moon mine and launch facility. 10 years to construct the habitat. That's our 20-year time frame. What do the people do? They would have to redo the factory, produce satellite solar power stations. 10 kilowatt power station, collect sunlight, convert it to microwaves, and beam it to Earth. What does it take to get here? This is the mass required to construct the habitat. Note, the majority of it comes from lunar ore. Only a small portion would come from Earth. Lunar mine. Results of the Apollo missions show that raw soil from the moon provides enough materials for the metals you need. Scrape it up, put it in a bucket, launch it from the moon. Electronic railgun. The electronic railgun is 15 kilometers long to reach velocity to escape the moon. The mass catcher looks like a large butterfly net. It'd be on the other side of the moon at L2. The machine shop comes from Earth. One side goes raw lunar dust. Out the other side comes metal, glass sheets, and the waste from refining would be used to form the radiation shield. The habitat under construction. Again, this is from the National Geographic article. What does it cost? Well, at the end of 10 weeks, we said $105 billion. But then somehow in the next couple months, they added a second mass launcher, but it got up there. Large transportation costs. The orange there is to get things to the habitat. The red at the end is the people and their possessions and the animals for the herds. This is the economics of the situation. Note, you're starting to produce satellite solar power stations before you ever occupy the space colony. You need the waste products from producing the satellite solar power stations to provide the radiation shield for the habitat. This slide shows the resources of space versus Earth. 1 square meters of space at Earth orbit is equivalent to 8 square meters of Earth for collection of solar energy. Note, the asteroids as a source of carbon, nitrogen, and hydrogen not found on the moon. In this view of the space colony economics, 3 colonies are produced and you're building power stations. In the early 70s, I would talk to my students about climate change. Some said dust in the atmosphere will cause the Earth to cool. There were glaciers over much of North America at one time. If the cooling people were right, this is what it might look like when the glaciers come out of Napa Valley and take out the BART station at Walnut Creek, California. The other school of thought said the Earth was going to warm. In the year 2200, what would happen when the last white-tailed deer dies in what was once the bottom of Lake Superior? In the year 2500, an alien ship might land on the Earth and ship a photo back home. I wonder what they would think when they see what Don Davis pictures as the last oil tanker on the shore of what used to be Lake Superior. Today, most scientists say that the Earth is warming, human activity increasing, burning of fossil fuel, releasing carbon dioxide and heat to the atmosphere. This from the Washington Post. The oceans also appear to be warming, again from the Washington Post fairly recently. Maybe alternative is available. In the mid-70s, Boeing was studying launching satellite solar power stations for Earth and concluded by the end of the century they would be competitive with Earth-built systems. This is a Boeing launch. This is a geosync orbit power station per Boeing. But if you had a space colony, it could provide Boeing with a satellite solar power station as it would be at the 10th of a cost for them to get it there. Did the Pilgrims send the Mayflower back to England to bring back bricks to build Boston? I don't think so. Let's build a bigger Taurus. This per Don Davis again. Maybe you could build Jerry O'Neill's Model 4 space colony. Twin cylinders, 5 million people in each of the cylinders. An interior view of a Model 4 space colony with the San Francisco Bay Bridge down in the distance. Maybe my great-grandchildren can look at the sky and see their source of power. What would you do with free energy? Well, you could convert hydrogen to oxygen. No more CO2. I live in Minnesota. You could heat the streets and sidewalks. No more snow shoveling. Maybe we might meet visitors from a foreign galaxy.
Just hip in the doorway with a shit-eating grin saying, geez, Eric, would you like to go to San Francisco? I got those space colonization